This video will go some more in detail about the general theory of systems beyond what we're covering here, what's needed for the course of things for this class. So everything we've discussed so far has been a two-component system because those are easy to handle, easy to draw, and sort of have nice properties when you try to write them out. But all the same ideas work for even larger systems of equations as well. So even if we have more than two equations and more than two components, we can still find solutions using eigenvalues and eigenvectors. If we have a real eigenvalue, we just find the eigenvector and build the exponential solution like before. For complex eigenvalues, you get a complex valued solution that you can then split into real and imaginary parts using Euler's formula to get two independent solutions from that complex eigenvalue. And if you have repeated eigenvalues that are defective, you can add in these t e to the lambda t terms with new vectors and these generalized eigenvectors to get to those solutions as well. So it's all more complicated because there's more variables, more equations involved, but the process here is all still the same. If I have n components, my goal is always to get to n linearly independent solutions. And the way you can think about building to this is that the characteristic polynomial is always a degree n polynomial. And then every eigenvalue will have some algebraic multiplicity in that polynomial. So our goal is basically for every eigenvalue to get a number of linearly independent solutions that's equal to the algebraic multiplicity in the polynomial. So for instance, if I have something like my polynomial here being lambda minus 1, lambda minus 2 squared, lambda squared plus 1, I want to get to 5 solutions here. This is a degree 5 polynomial, but it's all factored. I can see what happens. I need to get one solution from lambda equals 1. This one's pretty easy because this is a single multiplicity 1 eigenvalue. There's going to be an eigenvector, and I can use that to build my solution of the form v for that eigenvector, for eigenvalue 1, e to the t. The eigenvector is going to exist because it's a 0 of this polynomial, and we can work it out that way. The second, we have multiplicity 2, so we need two solutions. We might find two linearly independent eigenvectors. If so, great, we can do the same method from before. But if not, we're going to need to use these generalized eigenvectors and these t solutions, t e to the 2t solutions, to get there. So might need a t e to the 2t solution to get a second one. Because they repeated eigenvalue, it might not have two eigenvectors. If it does, great. If not, we'll need this extra solution here to do it. And the last term here is degree 2, but that's complex. So we need to get two solutions from the complex. It's degree 2 here as well. And because it's complex, I get these from the real and imaginary parts of the complex valued solutions. So even though things expand when you talk about bigger and bigger systems, the process is all the same. The general idea works no matter what. You're always going to be hunting for eigenvalues first. Then for each of them, you want to find as many eigenvectors as you can. For real ones, write those down as solutions. For complex, split into the real imaginary parts. And then for repeated defective, add in these t e to the 2t plus e to the 2t solutions to get to the full number that you need, the full number of solutions that you need to find general solution. And note that in cases like this, you could also have repeated complex eigenvalues. Right? That could happen if you've got a big enough system. And in that case, you're going to have t e to the t cosines, t e to the t sines. You're basically going to put t times the first one, t times the second one. You'll want to solve this out as complex values first before you take real and imaginary parts. So do the general solution and this eigenvalue stuff in terms of complex values and then split at the end. That's going to be the easiest way to solve it out. But you'll want t times the solution there as well. And then once you have these n solutions, you can provide a general solution and go about the process like you normally would. So there's just some more details on the general theory of system differential equations and constant coefficients in general, and how even though we're only looking at two-component systems specifically, all the same processes and ideas expand well beyond this to any component systems you want. The ideas are the same, it just gets more complicated because there's more components, but all the ideas still go forward to higher component systems as well.